All right, today we're going to take a journey deep inside, well, everything. We're going to dive into the world around us and even ourselves to crack the code on the fundamental blueprint for all matter. We're talking about the structure of the atom.
So let me start by asking you a really big question. What are you actually made of? I mean, really. If we could just zoom all the way in, past your skin, past your cells, what would we find at the very, very bottom? The answer is kind of simple, but also totally mind-blowing.
You would find atoms, trillions upon trillions of them. In the average human body, there are about 7 billion atoms. That is a 7 followed by 27 zeros. It's just an insane number to even think about. And it's not just you. The chair you're sitting on, the air you're breathing, it's all made of these tiny, tiny building blocks.
Okay, so what is an atom really? Well, the simple definition is this. It's the smallest possible piece of an element, like gold or oxygen, that is still, that element. Go any smaller and it's not gold anymore. But here's the thing. For the longest time, what an atom actually looked like was a complete mystery.
And that mystery kicked off this incredible scientific quest that lasted for over a century. You had these brilliant minds basically acting like detectives trying to draw a map for something they could never, ever see. So let's take a look at how that map, that blueprint, evolved over time.
Our story gets going back in the 1800s, but it really hits the gas in the early 1900s. We're going to follow 4 main players here, 4 scientists who each dropped a huge piece into this puzzle: Dalton, Thomson, Rutherford, and Bohr.
First up, we've got John Dalton, way back in 1803. His idea was pretty straightforward. Everything is made of atoms, and he pictured them as these tiny, solid, unbreakable spheres, kind of like microscopic billiard balls. It might sound simple to us now, but back then, that was a revolutionary place to start.
And for almost 100 years, that tiny billiard ball model was the best guess anyone had. But then, a discovery came along that changed everything. It turned out the atom wasn't some indivisible solid after all. It had smaller parts hiding inside.
This is where J.J. Thomson comes into the picture. He discovered the electron, a tiny little particle with a negative charge. So the old model had to change. He came up with what we famously call the plum pudding model. Just imagine a ball of positively charged dough, the pudding, and scattered throughout it are these little negative electrons, like plums.
The plum pudding idea, it kind of made sense, right? It seemed plausible enough. But it was about to get absolutely demolished by one of the most important experiments in the entire history of science, Ernest Rutherford's gold foil experiment.
The setup was brilliant because it was so simple. Here's what they did. They took these tiny positive particles, called alpha particles, and basically shot them like a stream of little bullets. Their target? A sheet of gold foil, so incredibly thin it was only a few atoms thick. And then they just sat back and watched to see where the particles went.
Okay, so think about it for a second. If the atom is really like that soft, squishy plum pudding, with all the positive charge spread out, what do you think should happen when you fire these positive bullets at it? They figure pretty much all the particles would just blast right on through. Like trying to shoot a tiny cannonball through a cloud of mist. Maybe a few would get nudged off course a tiny bit, but that should be it.
But what they actually saw, well, it blew their minds. Sure, most of the particles went right through, just as expected. And yeah, some of them were deflected a little, but then there was this tiny, tiny fraction, about 1 in every 20,000, that hit the foil and ricocheted. They bounced almost straight back where they came from.
Rutherford's own words on this are legendary. He said, "It was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." I mean, can you imagine the shock? Something was fundamentally wrong with the plum pudding model.
This crazy result led to the first mind-bending conclusion. The fact that most of the alpha particles sailed right through could only mean one thing. The atom must be mostly empty space. It wasn't a solid pudding at all.
So, what about those few particles that bounced back so violently? What were they hitting? Well, Rutherford figured they must have slammed into something incredibly small, super dense, and positively charged. So he threw out the old blueprint and drew up a new one. All the positive charge wasn't spread out, it was crammed into a tiny core right at the center, which he called the nucleus.
Now Rutherford's model, this tiny nucleus with electrons zipping around it, was a huge leap forward. But it still had a big problem. According to the physics of the time, those orbiting electrons should lose energy and spiral down right into the nucleus. But they don't. So along came our next scientist, Niels Bohr, to tidy up this part of the blueprint. Bohr proposed that electrons aren't just wandering around aimlessly. No, they're locked into fixed, stable orbits, or energy levels, around the nucleus. It's a bit like planets orbiting the sun. They stay in their own lanes. They can be in one orbit or jump to another, but they can't just hang out in the space in between. And this simple rule fixed that whole spiraling into the center problem.
So, when you put all of these discoveries together, Dalton's idea of atoms, Thomson's electron, Rutherford's nucleus, and Bohr's orbits, you get the basic model of the atom that we still use today. Let's do a quick breakdown of the final components. You can think of it as the atom's official ID card.
It all boils down to 3 key particles. Inside that dense nucleus at the center, you have the positively charged protons and the neutral neutrons. Then, orbiting that nucleus in those specific energy levels, you have the negatively charged electrons. The positive protons and negative electrons balance each other out, making the whole atom neutral.
So what makes an atom of gold different from an atom of oxygen? It all comes down to one thing: the atomic number. This is simply a count of how many protons are in the nucleus. That's it. It's the atom's unique fingerprint. Every hydrogen atom in the universe has 1 proton. Every carbon atom has 6, no exceptions.
The other key identifier is the mass number. Now, those electrons are incredibly light, almost weightless. So an atom's mass, its weight, basically all comes from the heavy stuff in the nucleus. The mass number is simply the total count of protons plus neutrons. It tells you how heavy the atom is.
So there you have it. We've gone from a simple, solid sphere to this complex, beautiful miniature solar system. But our journey leaves us with one final fascinating question to think about. If the atoms that make up you and the atoms that make up the wall right in front of you are both 99.9% empty space, why can't you just walk right through it?